Hello, this video is just a general introduction to the philosophy of science course. And the term science has two general meanings to it. Sometimes it's referred to as just sort of the results of science. That is, the things you find in a science textbook or the things that you're taught in a science class. And they say that's science. And that's a fine use of the term, but more often in this class, we'll talk about science as a process or a general method, an approach to understanding nature. And when we say understanding nature, we're looking at specific results of science that give us insight into what nature is and how it works. And so here's some of the main products that we expect scientists to be providing. Specifically, and one of the oldest products of science, would be predictions about what's going to happen. And so similar to predictions are counterfactuals. That's a term you maybe haven't heard before, but a counterfactual is rather than a prediction about what will happen based on the way things are, a counterfactual gives us a kind of prediction based on the way things might have been, or if things had been some other way than they actually are, then what would we expect to happen? That's a counterfactual. Scientists are also expected to produce explanations about the natural world. Why are things the way they are? Why do things happen the way they happen? What causes them? Ultimately, this can provide us, a certain level of ability to control nature, to understand it, to be able to live within it and make use of the resources, maybe even manipulate nature in some way to better serve ourselves. Some obvious predictions going way back into ancient prehistory, before anything was called science. Certainly planting, the time of year to do your planting and to do your harvesting, that was based on evidence that people gathered from the world, and it's pretty straightforward evidence. Often, where is the sun? What time does it rise? What time does it set? Where is it in the sky? Where are different stars and constellations and so on? Those are things that would help people to predict when the best time is to do different kinds of agricultural tasks. Certainly, astronomy was one of the very oldest sciences. So being able to predict exactly when different stars would appear, different times of night, different times of the year, knowing where the different planets are going to be at different times of the year in the night sky, when an eclipse is going to happen, that would be a good way to make yourself very famous, to be able to predict some dramatic astronomical event like an eclipse. So very carefully tracking the movements of the stars and the planets and the sun will help you to be able to predict these kinds of things. And then certainly, as we go further along in human history, using science and a better understanding of nature to develop all sorts of different kinds of technology and engineering abilities. So those are all very closely linked to science, of course. Now, a term that I often use to describe science, the process of science, is that it's an epistemically superior way of gaining knowledge and understanding about the natural world. And this term epistemically superior is kind of a fancy philosopher's kind of term, but it really just means that it's better. If we're looking to gain knowledge and understanding of the natural world, we want the thing that's going to be the most reliable way of gathering that knowledge and that understanding. And so science, it turns out, is the best way. It's superior, it's more reliable. We have more confidence in the conclusions coming from scientific research than we have just from, like what we might say personal common sense or folklore, some kind of past authority that isn't a scientist, or just our like strong feelings, the way we just think it must be. Those are very unreliable guides to the truth about the natural world. And so that's where science comes in. And that epistemic superiority of science is traditionally assumed to be based on these three things: the observable evidence, and then rigorous testing and logical reasoning. And we'll look at each of those three in a little bit more detail here. So first, observable evidence. Sometimes we refer to that as empirical evidence. Evidence is empirical, or an observation is empirical when it's based on our sensory systems. So we've actually observed it, we've heard it, we've felt it, we've tasted it, whatever it might be. Empirical evidence comes from, hopefully, as much as possible, a clear and unbiased use of our senses, right? We want to set up our observational circumstances that we're getting a very clear perception of what's actually in front of us. Second, it's got to be public. That is, everybody has to have equal access to it. That is, if we sort of all gather around some bit of evidence that's sitting there on the table, we can kind of all agree that, yes, this is what we're observing. It can't be something that's just private to one person or a small group of people. The community of scientists just won't accept that kind of evidence if it's only accessible to one person or a small group. Of course, the observational evidence has to be measurable in some way. Hopefully, the measurement is quantitative. That is, there's specific units, a measuring device that we're using, and we come up with specific units like grams or meters or something like that. So we have a number that we can use and say to refer to. Also, we sometimes might use qualitative evidence, which doesn't necessarily have a number associated with it. That's something is, maybe certain colors, although nowadays we certainly can put a specific number on the wavelength of light that's involved, but otherwise it would be sort of more intuitive and a little bit more subjective evaluation of something. That's a qualitative kind of evidence. What's the quality of what we're looking at, rather than the specific number of units involved coming from a specific measuring device. And then finally, in order to be good scientific evidence, the observational evidence has to be repeatable. It can't be just a one-time thing. That might be something interesting. It leads us into a further investigation if it's just a one-time thing, but we can't rely on that as good evidence to support some kind of scientific conclusion if it only happens once, or just so rarely that we can't make a firm conclusion on it. So the assumption then, and this is an assumption that we will actually challenge throughout the course, is that as long as things are set up properly, right? As long as our observational circumstances or our experiment is set up properly, then everyone will agree on the observed evidence. This is the public aspect of it. We all kind of gather around and we're like, oh, yep, that's what it is. We all observe this and perceive it in the same way, so we can all agree as to what the actual evidence is. Okay, moving on to rigorous testing. We'll definitely talk a lot more about this later on, so I'm not going to spend too much time on this here. Typically, rigorous testing is going to involve some kind of experimentation, one in which you can control as many of the variables as possible. You might even have a control group and an experimental group. Just like with the observational evidence, and this is closely linked to observational evidence. In fact, the rigorous testing is trying typically to produce observational or empirical evidence for us to use in our conclusions, but it should be repeatable. It should give us the same or almost the same results every time we run the test, and it should be consistent. We should run the test in the same way each time to produce those repeatable results, but then also we should do it under varied circumstances. If you're only running a test under one set of circumstances, then you might really only be finding out what happens under those circumstances, and that's it. That can be interesting, that can be a valuable scientific insight, but nevertheless, if you really want to gain a full understanding of nature, you need to run your experiment under different circumstances to find out what's really going on and how it can change, and how the results might vary depending on how you change your variables or conduct your experiment under different circumstances. So here's an assumption that was very common. In fact, many introductory science textbooks in the first chapter will present what they refer to as the scientific method. And that might even be presented as a kind of flow chart that scientists go through to stick with the scientific method. And the idea might be that if you're not doing things according to the scientific method, then you're not really doing science. That's a widespread assumption that we will examine in this class. Finally, linked to the first two things is logical reasoning. How do the results of your experiment logically support or undermine your scientific conclusions? Are you able to take the evidence, the observable empirical evidence that you gathered through your rigorous testing, and use that to logically support one specific conclusion? The thought was, a general assumption is that science follows a very strict kind of logic, and we'll look at that very closely throughout the course. But when we're talking about supporting specific scientific conclusions, I've got some examples here. These are sort of general statements about nature. We might call them theories about nature, about the way nature is and the way nature behaves. So we might gather a huge amount of evidence, run a bunch of experiments to produce empirical evidence to support the conclusion that all metals expand when heated, or that all stars contain hydrogen primarily, or that all fish have gills. So these seem sort of intuitively obvious, perhaps, once you've gathered the evidence that these are the proper conclusions. But when we're talking about strict logical reasoning, how exactly does that evidence support those conclusions? How strongly does that evidence support those conclusions? These are things that we'll look at in the course. So when we do look at those three elements of science, the three pillars of the epistemic superiority of science and understanding and gaining knowledge about nature, we will question how reliable those things really are. We'll find out as we go through the class that perceptions can be pretty inconsistent and unreliable. They might be very different from person to person, or within one person from one time to another time. They might perceive things differently. And if there's no agreement as to what people are perceiving, then there's no agreement, perhaps, about what the actual evidence is, what the empirical evidence is that we're using to support our scientific conclusions. That could be a problem. Testing procedures can be very complicated and very diverse and very difficult to understand sometimes for the non-expert. So it might turn out that there isn't one specific one specific procedure that is the scientific method. There might be a wide diversity of different methods that scientists are using. Does that cause problems for science? Does that undermine the epistemic superiority of science? Well, that's something we'll look at. Plus, scientific reasoning, as we'll see, is difficult to fit into one specific kind of standardized, rigorous, logical procedure. There's not always like a very clear logical support for scientific conclusions based solely on the empirical evidence that's been gathered through rigorous testing. So there's reasons to question all three of these aspects of what makes science epistemically superior. Nevertheless, and this is a big take-home message of the course, is that science is successful. Despite any of the worries we have about it, any of the problems that might arise within the scientific process, science just is successful. That's sort of just a given. But why is that given? How do we really know that? Well, science has provided us with successful predictions, going all the way back to the astronomical examples that I gave before, things like predicting eclipses, when the seasons are going to start and end, and all of those sorts of things. Science has given us really, really amazingly accurate predictions over the centuries, over and over and over again. Of course, it sometimes gets things wrong, but the fact that it gets things right so frequently about very complex aspects of nature gives us good confidence that science is on the right track. Despite any problems it might have, science is reliable. Then, perhaps even more dramatically, is all of the technology. I mean, this technology that I'm using to produce this video and post it online, I mean, where did all that come from? It came from scientific research. If science wasn't reliable, if science wasn't an epistemically superior way of gathering knowledge and understanding about the natural world and how to manipulate it and how to work with it, then it'd be just sort of an amazing coincidence that all of our technology works so well. You know, airplanes fly, right? Why do they fly? It's like, well, because hundreds and hundreds and hundreds, thousands of people put in the work, the scientific work to understand, you know, fluid dynamics and the shape of wings and fuels and engines and all of these things to make it actually work. So the technological applications, the success of the technological applications is by far the most dramatic example, making it very clear that science actually really works, despite any problems that science might have, despite the fact that maybe science isn't always 100% reliable in all things. Nevertheless, over the long term, science clearly works really well. And then associated with all of this is the fact that science makes such dramatic progress over time. With the successful predictions and our technological applications, these have just become more and more dramatic over the centuries. And in fact, we're sort of the pace of progress in science has only accelerated over the centuries as more people become involved, as we learn more and more about how nature works, what nature is actually made of at the most fundamental levels. Scientific progress has only accelerated. So these are the reasons for thinking that science is successful despite any of its problems. Now, speaking of the problems, here are a few of them that we will talk about. Sometimes old ideas get in the way of new understanding. Scientists are humans, right? We get used to thinking a certain way. We get comfortable in our beliefs and our way of understanding and our way of approaching our work. For scientists, they get very comfortable with certain theories that they really understand at a deep level and have been very successful for them in their careers. And when that happens, they get kind of entrenched in their pre-existing beliefs. And as humans, they are resistant to changing those basic beliefs about how nature really works. So sometimes that gets in the way of scientific progress. Similarly, personal biases can get in the way of us being unbiased observers of nature and in how we design our experiments. Some of that can reflect our personal biases or our cultural biases, and this can sometimes get in the way of us having a clear insight into what's really going on in the natural world. And then at a practical level, science is expensive. It takes funding, right? Somebody has to pay for all of the scientific equipment and experiments and supplies and salaries for the scientists and the engineers and the staff to actually make science work. It's very expensive. And so there are funding agencies, the National Science Foundation, the National Institutes for Health in the United States are the primary ones that fund most of the scientific research that happens. And so there's not unlimited money. So there are people that are in charge of deciding what gets funded and what doesn't. And sometimes that can be biased. They will tend to provide funding for scientific work that they think is more likely to produce success. Well, that makes sense, but the people making those decisions have their own biases, their own pre-existing beliefs about what's more likely to be successful, what's more likely to lead to new technologies or whatnot. And so other areas of research, other research programs might not get much funding because the people in charge of providing the funding just don't think that that's a good area to be sending resources toward. Though it might turn out in later years that they should have because it produces huge breakthroughs, new technology or new ways to solve some of our outstanding problems.